I want to talk about design synthesis, geodesign synthesis. How do you put things together, and what is the implication of that? And for the last year and a half, I've been working with Rishi, who spoke last year at this conference, on developing software basically for geodesign synthesis for large problems at the early stages of design, at the early stages of planning, deciding what to do. And we've used his software in 5 workshops. The fifth of them was this morning, in which about 20 people from Esri and from colleagues from other universities and other places worked in teams to design for the case study on Soma Japan that those of you who have heard me speak here have seen several times before. And things went wrong. We had a lot of circumstances where information was dropped, just disappeared. It happens. It didn't happen before to us, but it happened. Things disappeared. And there were some problems, bugs of various kinds, which I have no knowledge of, but he does. And those have been fixed. So what this talk today is going to be is a series of projects starting in 1967. A long time ago, but that's how it is. That's how it is. And we're going to describe live the demonstration that we did this morning. And what Hrishi's going to do is go through the capabilities of some of the capabilities of the software that the group was working with this morning. And I'm going to interrupt him every once in a while. And if it works, it works. And if it doesn't work, too bad. It'll work next time. And then I'm going to end with some observations about why this kind of approach is useful. And it's not that far from what Greg and his team are doing here. I know that. I mean, we've been colleagues for a while. And it's actually pretty easy to use, but it requires experience and knowledge, which easiness isn't a substitute for, right? So realize that we're doing something live. It's unrehearsed. My part of the lecture is rehearsed. I did it in my head. But the real stuff that is interesting to the people who are in the business that many of you are in, from the company and other companies, or those of us who teach or practice, that part is live. And if it works, great. If it doesn't work, also great, because we know what we can do about it. So I'm going to begin. First of all, thank you all for coming. It's really nice to be able to speak with Rishi on the one hand, but not speak with a tight time limit, which is the advantage of the time that I've sort of taken with Shannon's help. Geodesign needs a lot more experimentation and the sharing of our experiences. I've been involved in 150 geodesign projects, starting 50 years ago. These projects fit all the definitions that any of us have put together. And I've never done the same thing twice. And what I want to do is make that point again and again and again. What you need is a set of tools that are adaptable to different ways of working. It's not one way of working, and it's not one set of models. It's your models for your problem, your way of working, more or less, but in a set of tools that are open to that and that work easily, smoothly, and are actually quite easy and fast to learn. And nobody is saying that what Rishi is doing as his doctoral thesis at the Center for Advanced Spatial Analysis of University College is the best one. It's certainly not the only one. I know a half a dozen teams who are doing similar types of R&D, research and development work on geodesign synthesis, including at Esri. And I think that all of them will be obsolete in a couple of years because the technology and the thinking and the experimentation the half-life is not long, okay? But the principles probably will last a very long time. That's why I want to start with a project in 1967. I drew this diagram in 1966. This is what it says. A lot of people have seen it because it's in my book, but nobody's ever looked closely because it's too small in my book. You have to know the site. You have to know the site. That's an interesting point, because I don't think it comes from remote source. It comes from being on it and remote source data. For any design, you have propositions, you have a program, you have proposals. In other words, I'm not focused on knowledge. I'm not a scientist. I want lots of scientists and others. But I do need to know what we're trying to do. I need values, I need objectives, I need requirements. They don't come from me, they come from those people. And I know that a proposal has to come out the other end. In other words, regardless of how many designs we test and try, somebody has to end up doing something. And that requires somebody to believe that a proposal is a good idea. At that point, computing was based on grids. There were no polygonal databases, none. Or if they were secret. It begins with the decision processes. I grew up in an academic environment where the decision was made at the end of the study. And I knew that was wrong, because the students were wasting their time, and then the jury would decide whether it was a good design. Nobody interviewed the jurors before they started the design. Nobody had a clear idea of what a good design would be judged against, or as, and why. So you have to understand the decision processes, and it's plural, because I knew that there wasn't just one, and that people disagreed with each other. And the problem of geodesign is make them agree. So the idea that disagreement becomes agreement is at the core of how geodesign has to work. I didn't believe the popular theory of the day that the environment governed development, that there was such a thing as inevitable patterns of development. I didn't believe that at all, because it denies engineering. And I thought we had a difficulty because we had two streams of analysis. One is the site, and there's a data bank. All right? That's a shared GIS, if you wish. The site, it has site systems. There are many of them. See that? That's many. They each have a vulnerability. And at the same time, there's a demand set of systems with many land uses, as many as 20. And that they're looking for locations, and they judge locations by their attractiveness. They could do it by repulsion, but they don't. It's probably by attractiveness. And that there's an inevitable conflict between these two that have to be resolved in a design. There I used the word plan. I regret that, but I used the word design as a verb. And that design has to be judged by its impact in a simulation model. And it has to feed back. And furthermore, it has at least 3 scales. Those are scales. 1 to 2.5, 1 to 25, and 1 to 250. And that you needed a combination of the site systems, and the demands at any given time as the basis of the simulation model. That's exactly what I wrote a book about 3 years ago. It's that diagram. Except it became the basis of my Theories and Methods course, in which I taught Theories and Methods courses about every one of these steps. I had shared an office with Peter Rogers, who's an engineer and an economist, and a water engineer. And he and I talked every day. And we decided in 1967-68 to run a graduate studio on Boston, this part of Boston, and that we would build 10 models, computer models. Population increase, leading to new industry, housing, recreation, and commercial centers and institutional centers, which change transportation, which are assessed by effect on local politics, local finances, visual quality, and water pollution. If it passes assessment, we move 5 years into the future, and we cycle for 25 years, updating the data as we go. And if the answer is no, we feed back, and we can feed back to any piece of this. That's 1966, 67. And then we collected a bunch of bright graduate students, about 12 as I recall, and we gave each student one of these models, having shared the creation of a GIS, which at that time, as I recall, each pixel was probably something like 1/4 of a mile square. And it was hand-coded from aerial photographs and from maps. It took a long time. But we knew the data that we wanted, and because data was so expensive in human labor, we took the least possible data to do this task, and everybody had to specify what they needed. And then every bright student was given a question. And there's a bright student. And his question was this. That's the Charles Elliott plan from about 1910 for the open space of Boston. And now we were in 1968, or I think 67 or 68. And the question was, where should we put open space given that Boston has grown and it's likely to grow a lot? And so he had to make a model of every step of an analysis that says this is where we should put open space. And that's a regression analysis of access to open space. That's 1968. And that's Peter Rogers and I, that's me, taking the students' models and putting them together in a flow of information. And that's the flow of information. Every one of those is a modeling step. And then we used a human agent-based model, because what Jack and other students had to do was compete for land. Either the housing people get it or the open space get it. It's as simple as that. And maybe the shopping center gets it. That's what they did. They were competing for land based on the analysis of what they thought they wanted to get, updating every 5 years. And how do you compete for land? Well, you figure out how much you need, you color code it, you take a pin, and you put a pin on a piece of a map. And that's basically saying, let's protect the harbor islands, which now is a state park. What's different? And that's the final design. And my colleagues had no way of understanding it. Nobody could understand that and say, that's a good design or a bad design. But that's the design. The students knew it. I knew it. The faculty didn't know it. And we evaluated the impacts of that against their models and had a very interesting discussion. Realize that in 1967, we had a rule-based design by Eric Teicholz, with a little advice from me, of automatically locating 4 kinds of houses, trees along a road and not in the water, roads in parallel, and the houses connected in various ways. That's a site plan for housing of 4 different kinds of housing with a rule-based design done in about an hour of extremely expensive computer time. Now, we couldn't link that analysis technique with the first one, which was a human agent-based model. Furthermore, by 1967-68, we could rotate landscape with very expensive symbols. We could automatically locate houses and trees on a terrain model so that they roughly matched. And we could animate in very expensive, ugly drawings motion through that landscape. That's 45 so years ago. So, there's your city engine. What's different? I had decided long ago, because of my background, academic background, that these problems were, I can do that, but I don't find it useful. That this is where the action is. And let me digress. The World Bank's analysis is that in the next generation, at least half of the world's urban growth is going to be in cities between 1 million or so. And after about 5 million, they get really hard to plan. And so this bigger scale is where I think a lot of the action is going to be, and it's necessarily going to be collaborative. And I learned that long ago. I've been involved in 150 projects, some as teacher, some as consultant, some as leader of a team or a member of a team. And after a lot of time, I decided, and a lot of coaching from Jack and Laurie and a whole bunch of other former students, I decided to write this book on a framework for design. And I'm not going to go through that now. But I can tell you that I always saw it as an issue of collaboration. Now, there are things that I learned about workflow during that process. In the third iteration, when you sort of know why you're going to do something, and you sort of know with your colleagues how you're going to work, you have to do it. And that these people are really important because they don't agree with each other. And you have to bring them through a process iteratively until they do agree, or they throw you away, one or the other. And you're going to have requirements. They're going to require data. They're going to require a set of process models, each of which has an evaluation model. And what's a big problem is that the science and GIS community either thinks or is made to think that their work stops here, and that some other group of people, like designers and planners and those engineers, they start with your evaluations, and then somehow or other they're going to go from the present to the future and make a design. And I think that's wrong. So I think that the people who know the most about the problem ought to be contributing the ideas that help their system. And that we need a set of techniques and a set of software to allow us to use that and synthesize it into a new design. I don't know anything about nuclear radiation. I learned fast from people who do. So nuclear radiation is one of the things in the design issue. I think that blurring of that boundary is the most important thing that we've learned, at least I've learned over the years. So basically, we have to move through the past to the present with data, process, and evaluations. We know there's a history. We know there are constants. We know there are requirements. There are lots of ways to get through this, and there are billions of ways of combining these. And what we need to do is get fast to eliminate them so that we have a handful that we can think about. And I've shown this before many, many times. There are lots of ways to get through. Now, the Redlands experiment is really important, and it's getting more important over time. This was the project that Jack and I talked, and we said, what we ought to do is do an experiment in which teams use different ways of designing on the same problem and see which ones work. And what we decided was we would work on 2 scales. One is an open space plan for Redlands as a city, and one was a development around the new transport, rail light transport system that eventually one hopes will get to Redlands. And we used a workflow that had GIS here to this point, and GIS from a design to evaluate it, but not necessarily in the middle. So we had a team that had 2 tasks, and they were assigned one of these ways of designing. Redlands University and Esri, in some combination, built a very sophisticated computer support system for this. Every design move made by any of these teams was recorded and evaluated. That was an extremely important experiment that nobody gets enough credit for. I actually don't know exactly who did what on it. I used it. So here's Ron Uzumida working in the anticipatory thing. That's his design. That's his conceptual design. And he made several versions of it, and we recorded whether they got better and better and better and better and worse against a set of models, computer models, for the requirements of that particular design. And what he's doing is drawing on paper, and somebody else is digitizing it. In the middle, you have the combinatorial scheme. What they're doing is they're taking little tiny diagrams, the diagram that relates to access, the diagrams that relate to facilities, the diagrams that relate to water, and they're combining these diagrams to make a design. And this design is Kevin Johnston and his team, and they made, from my knowledge, the first agent-based model that started out as a random design, and as it iterated many, many times, it got better and better and better and better, and that's their final design. In 3 dimensions. I've never seen that before, and I don't think anybody's ever done it before, but it was done. Now, we tracked these designs, and we compared these designs. And we knew, for example, what was consistent was that the first design was not the best design. Now, almost everybody who does planning and design thinks their first design is wonderful, and everything else they're doing is making it better. Well, everything else they're making is necessary. The feedback system mitigates against a bad strategy. And so there's a process of improvement, but then if you do too much, there's stability and then there's decline. Their last design was not their best design. Their third design actually was their best design. So the idea of versioning is terribly important. You have to version them and you have to keep them, and you have to compare them. And what we found that was really important was that some of the methods got worse as the problem got bigger, and some got better as the problem got bigger. In other words, we're not sure, for sure we're not sure, but size and complexity and scale do matter in terms of the probability that you're going to have a good design coming out the far end. So that raises a very interesting question. What way of designing should we use given the problem we're faced with? It's not one way, that's sure. But which way should it be? The methods that they used were different. The methods for anticipatory, participatory, and sequential were basically serial sketching. I make my move, I make my second move, a third, fourth, fifth, and I come out with a design. If I vary the first move, the design might still look very similar, but it got there a different way. And I can keep the same move, vary the second move, and it might come out similar, but quite different. That's not the same as that. The ones working at this scale, which is we were here in one project and there in one project, they were based on combining diagrams into a design. And the rule-based people were terrific because they were working in this scale well by doing this. And Kevin was remarkable by building at this scale with a rule-based system. But it's an outlier. And in general, let me go back. In general, what did I do here? Go back. In general, and I'm guessing from a sample of one experiment, only one experiment, I'm guessing, the diagram-based systems are likely to be better in this middle scale, middle size. Likely to be better, not guaranteed. But who knows what the problem you're faced with is. Now, the first project that I did in diagramming was in 1986. That's a long time ago. And this is one of the case studies in my book. My students went to Bermuda because the prime minister grew up next to the dump, and that's the dump. And they interviewed lots of people. This is the Royal Gazette dump study team listens to the people. That has never been done before in Bermuda. And they made this diagram, which is a set of constants that every design has to have, and a listing of 17 systems in the order of importance. So that's the most important, second, third, fourth. And they made a set of diagrams on how do we help that system. Right? And each student was forced by me, to pick a different set of diagrams to make a design. And we had 12 of these designs in exactly the same graphic language. Imagine it's City Engine, for example. But we built a model. The models were put into a box, and they sent to Bermuda, and they said, we like 3 of these, the rest you can take them away. So the students had to coalesce in 3 teams, Team A, Team B, and Team C. And then the Prime Minister invited us back, and we made a lot of presentations, and the people voted, and they voted for this design. And that design was the most important diagrams and the #1 choices of consultants on how to put the thing together. So the student who picked first, the red student, basically won a popular competition. That was very important. That was very important, that the students who worked on the things that were seen to be most important first and let the rest follow won that experiment. Even though somebody may have been really interested in something down there, I told them, don't do that, don't do that, don't do that. Don't waste your time on things that are relatively unimportant, knowing the decision model. Now, I've used that technique many, many times, and I'm going to show you 4 of them. I've run 80 workshops at universities over my career, 80 of them. They're all on real problems with real people. Sometimes they're students, but they're real problems. This is the smallest problem I've ever worked on, the smallest, using these techniques. This is the redesign of the Taiwan Air Force headquarters, which is being moved, and it's the #1 development site in the city of Taiwan. It's 15 acres. And there it is. It's surrounded by housing. That's the chief planner of Taiwan. That's the site. It doesn't matter. There are a series of evaluation maps. These are hand-drawn. There's a set of diagrams of how to help history, how to help ecology, and how to help traffic. The students put them together as graphic diagrams on plastic, but eventually they were encoded for City Engine. And we had the Esri Taiwan City Engine team working with us, and they each made a model of the designs, and there was a process of consolidation and negotiation, and that was the negotiated solution for the group of students who were representing city government, local government developers, local owners of property, industry and education, and environmental NGOs, who didn't agree at the beginning. The second project is maybe the most politically complicated one. Go back. This is a workshop done that Tess and I ran for 14 universities in Turkey, all gathered all around the Ankara region. The mayor of Ankara has a master plan. And it's the southern expansion of the city, and it's about 200,000 people. And the problem is that there's a river corridor with lakes and open spaces that goes like this, and it's right through the city, and it's really, really important. And the problem is that this is an area that was settled by squatters, immigrants, and they built their own houses. And they're actually perfectly okay. But he wants to destroy them all and build high-rises. And he wants to not follow the regulations of the city. So we created 2 teams, one which follows the existing laws and one which says, no, you can do whatever you think is better. And we created the teams so that they each produced 3 time stages for 20,000, 100,000, and 200,000 people. And we did that, again, by hand, with City Engine behind us. So at the end of it's a 2.5-day workshop. So at the end of the first day, we had a set of 6 designs in City Engine and in hand graphics, not GIS. They were encoded. And then we made those groups make one plan, and then we considered the question of, are they really different? Is this really different from this? And they did a negotiation, and they came up with a final recommendation which says, don't destroy these houses, just build a new community right down there next to the lakes. That was the answer. Now, whether the mayor likes that or not, I have no idea. I'm going to skip that one. The final one is one that I spoke about last year. It's Soma, Japan. There was a tsunami that in that town killed 1,000 people. This was 3 years ago. And Eric Whitner and Shannon were in this workshop. And that, in part, caused the nuclear disaster in Fukushima. And the city of Soma is the city right next to Fukushima. And during the nuclear disaster, everybody left. And the problem that the mayor has is the old people came back, but the young people didn't. And he's got a dying city. And the question is, what to do? And he asked the local university in Sendai to study that question. And these are people I've worked with for 15 years, with Stephen Irvin and Mike Flaxman, And they know GIS and they know my framework. It's been in Japanese for 15 years. Now, these are geographers and engineers and a couple of landscape architects and urban planners, but they're mainly geographers and engineers. And these are hotshot GIS people. So in 2 hours, they put together 10 models: ecology, earthquake damage, flooding from tsunami, nuclear radiation, evacuation, replacement housing, high-density housing, low-density housing, commerce and industry. And after they did these evaluation maps, they switched to hand graphics because we had no software to support this. I knew of Esri's system, but this is before that. I knew they were thinking about it from Mike and from Bill, who I've known for many years. But it wasn't available. So they switched to hand graphics on how to improve it. They made their plans by merging these diagrams. They scanned them. They digitized them. And so that's the first round of designs. That's the second one. It's already digital. That's the third one that's digital. They had a whole bunch of impact models. And then Eric Whitner, on the fly, turned it into City Engine, and there's a flyover animation. And that was done in 2 days. 2 days. I showed that lecture at CASA, at University College London. And after my lecture, Rishi, who I didn't know, came up to me and he said, just out of the way, this is what Carl, I think that could all be digital. And I turned to him and I said, I do too. And then we started to talk. And it turns out Rishi's a mechanical engineer, graduate of Michigan and MIT. And he grew up in Japan where design is done collaboratively. And he worked for Honda in America, and they designed their cars, but all their parts and machine tools collaboratively. And now he works in Dublin for Microsoft, matching software to industrial needs, and he's a PhD student at CASA. And for the last year and a half, we've been meeting regularly. He knows software, and I sort of by now know a little bit about synthesis. And we talk, and I say, these are the things that I want to do when I'm doing this kind of work with my colleagues. And he comes back shortly after and says, well, here's one way to do it. And we've done this now in five generations. Right now, it's pretty stable. You know how to collect data, although that's changing. You know how to make process models, although that's changing. You know how to evaluate, that's okay. Then there's this void. Then you know how to do impacts, that's roughly okay. And you may have to learn how to talk to people about this work. That's not easy. But it raises the kind of question, what kind of digital information management support are needed for geodesign workflow, and especially for the change models in geodesign collaboration? Part of that is how do you compare many designs, which I'm going to talk about at the end. Now, one of the things that we met on early, as I said, look, these are the characteristics of geodesign problems. They're complex with at least 10 systems, not one at a time, but 10 at a time. Each system has data, process, and evaluation models. There are many ways to change and improve each system. Imagine there are 10 models and 10 ways to improve any system. That's 100 diagrams. You need to be able to handle 100 diagrams. Change toward a design is a relational synthesis in space and time of sets of system changes. We want to be able to take groups of things and move them together through a process. Each change move has impacts across all systems. And there's an enormous problem. There's a chicken and egg problem. Which comes first, the shopping center or the road? The sequence matters. There are many ways of synthesis of making a design. Some are more effective than others, depending, but I'm not sure what the dependencies are. We've only had one experiment. All changes feed back to representation process and evaluation models. There are variations based on design revisions. There are alternatives based on different decision models or different assumptions or different scenarios. These have to be compared, and usually, but not always, one has to be selected for presentation and implementation, maybe. Implementation in the future changes everything, changes the data, the representations, the evaluations. And a summary statement, synthesis in geodesign is not a linear process. It can be, but it probably isn't. The methods and models do not scale. That's really important. But they must interact and be selected across the problem, the geography, the size, the scale, and the culture. And now I'm going to turn it over to him to show you version 5, and then I'm going to take it over at the end. and I may interrupt him on occasion. Rishi.
Thank you very much, Carl. My name is Rishi. I'm a PhD student in CASA. And before I start, I want to acknowledge Mike Batty, who's not here with us, who's my primary advisor, and James Cheshire, who's way at the back visiting us from London, and he's also my secondary advisor. And it's really great that they're here, in addition to Carl. What I'm going to talk to you about is the framework and how I saw the framework and where it's going. This all started maybe 2 years ago, so I've been at this for 2 years, 2.5 years even. And what you'll see in my short presentation is the work that happened today in the morning. There were about 20, 25 people who worked on the SOMA case that Carl talked about.
If anybody who was in the workshop this morning, would you raise your hand? Look around you. Those are the people you can ask questions at the end of the talk because we're going to dinner. But those are people who can say it either worked or it was crap. That's up to them, all right? But those are people you can ask.
So what this diagram shows is basically how the geodesign process, and in particular the workflow that Carl describes in his book works. You start at the very top with representation and process models. Then you have, from those process models, you build evaluations. And in the case of some of his case studies, there are simple red, yellow, and green maps. And then based on those evaluations, you come up with ideas, projects, or policies to kind of have your change. And then you do the synthesis where you pick and choose individual diagrams and kind of come up with a plan or a set of plans, and then you analyze them to get feedback and you progress. And the whole key to all of this, which is what I highlighted in my kind of little lightning talk last year, is that the notion to move very, very quickly through this framework is the key. And the other problems are kind of solved in some ways by now. And so if you kind of look at my thesis in particular, what we've tried to do was to solve the quick iteration, moving through this workflow extremely quickly. By extremely quickly, I mean we've done experiments over the internet where people start from absolute zero, not knowing or even having a login, to me training them and them coming up with a design in less than 3 hours over the internet and all the problems that's associated with that. And so that's the workflow really is my thesis, which enables people to come together and move through Carl's framework, those boxes that you've seen. I'll show you a little bit in the next few kind of screens. That's what we've solved, or at least I've attempted to solve in the last few months. All of this will be available publicly after July, which is when I finish my Viva. And it has all the self-help documentation, so anybody who wants to use this will be able to use it. And it's certainly my aim is to have it available for anybody in any part of the world to do this kind of quick iteration, do design at an early conceptual stage using the tools. So what happened today in particular, and the focus of my thesis, is around the red box that's shown here. You start with evaluation models, which are simple. Well, before that, you start with requirements for a plan, and usually the tool you will see has 8 to 10 requirements, and that's mostly out of practice and kind of experience that 8 to 10 systems is the kind of the optimal number that you should probably think of. If you look at Carl's diagram in the first slide that he drew a long time ago, if you think of 5 vulnerability requirements and 4 or 5 attractiveness requirements, that's kind of the base of all of this. You then have the diagrams and the synthesis, and you also have various ways of actually coming together and making a design or making a plan. We've actually have enabled almost 4 or 5 types of ways to design, and we're testing 3 or 4 more, and I'll show you how all of that works. And finally, basically, when you build a design, you can very, very quickly assess how good or not good the design is with different systems. And then you progress. So the interesting thing about this space in general, that it is not GIS, it is more like design. And so luckily for us, most of the GIS formats are kind of supported. So you can have shapefile for your models. If you have GeoJSON, drawings, well-known text, whatever, you can use that as an input into the system. And then we've already shown you can use the outputs as a shapefile, which then goes into SETI Engine or any other visualization tool, or you can have it as GeoJSON and use it on the web or whatever. So the idea is to create this kind of a system which takes in any file format and you can take out all the data in any way. And that's what kind of you'll see. At the back, though, there is very advanced versioning that's going on, so it kind of understands all of these formats. I want to talk a little bit about the collaboration, because that is the most critical piece in my mind, and a technical challenge that certainly keeps me up at night. There are many modes to collaborate in the tool, and we've tried a few of them. But fundamentally, when you are a part of a project, you can really be three kind of personas, if we can think of it in that way. You could be an administrator, you could be a team conductor, or an individual person, and that hierarchy is shown over here. Basically, the idea is to kind of split yourself in different kind of roles as you progress in the workflow. And that's kind of, I thought, was very critical, because usually you might have somebody who's an expert take on a role of maybe a non-expert. And that gives rise to very interesting kind of ways to design. You can do many, many ways, and we've set up a couple of them for sure. You can have an open collaboration mode where everybody is on that on the workflow. You can have a competition between teams where you can say, you guys are competing with this other team, and that's what happened in the Turkey kind of workshop that Carl described, where somebody was following the laws and they were competing with people who weren't following the laws. So you can set up projects like that in the tool. And also you can have competition between the coordinators and have participants as anybody on the internet, for example. And this is kind of a crowdsourced design type designing, where anybody can come in, make their selections, and then the most popular design may be the one that wins. But all of them really work in the same framework of representation, process, and evaluation, and then synthesis. So that is really the key idea for this, where the data is separate from the framework, and that's where a lot of my time goes, where you don't try to mix data with the framework. So you can bring any data, any model. If your model can make a map with 3 colors or 5 colors, it should be okay, and it could be used. Like I mentioned, once the synthesis is done, there's ways to compare different designs, which was the one you can compare it through many, many different ways. What is the impact on the systems? And you can come up with alternatives fairly quickly. We've gone through workshops where people create 2 to 3 versions of their plan, iterating over a period of 1 or 2 hours, and you can see that the second or the third plan is far better than the first, and certainly the conversations in the teams are much different when you do the first one and then jump onto the second. I wanted to kind of just talk about the history of it a little bit, because that's kind of interesting for me, at least. So this was the first one which we did in July, actually. Oh, no, that's July. Yeah. That's Mike at the bottom there, and this was done in CASA in London, and that was the first version which we really broadly tested. And that's some of my colleagues. That's James in the middle over there. Then we did a second experiment in the Geodesign Europe conference in TU Delft, which was the same SOMA data set. But in this case, you had professionals and very, very senior professionals who were sitting on desks and kind of doing this kind of work and design there. We then tried a couple of internet-based workshops where people, this is one that we tried in CASA, that's some of my friends in CASA, basically, and people logged in from their desks, and some of the others, I don't see Eduardo here, but a few people logged in from Amsterdam and collaborated to build a design. And we did, finally, in November, a really long-distance one where we had people from all of these locations, from Boston to Tokyo to Beijing and Hong Kong, and parts of Europe to come together on the tool and using Skype, create designs in 3 hours, less than that maybe even. Yeah, and that's the same thing we did today. So today we had people from other parts of the US, from Turin, who joined in and tried to create a design on the tool. And here's how it works. Basically, you can start a project, and that's me and Carl working in CASA, and you kind of give a quick introduction over Skype, and they start with the design. And here's an image of him giving the introduction to the people, and he's talking to people on Skype. And I want to focus on that little circle there, because that's what you're going to see. And so what's going on there is how this framework looks as a tool is what you're going to see. Every project has some requirements that has R written on it. The R1, R2 is basically a set of requirements. And these boxes are individual diagrams, and you kind of navigate through to come up with your design. I'm going to switch to my browser here. And I'm just going to walk you through very quickly the main screen. And so this is data from the workshop in the morning. And so, like you saw, this data was provided by the colleagues in Japan. You have the 10 requirements. It's abbreviated. So this is ecology, quake, flood, nuclear, evacuation, and so on, low-density housing. And these are simple 3-colored maps. And what produces this maps is kind of not a concern of the tool. So you could have a supercomputer producing it. You could sketch it by hand. You could have some person who's really experienced in this, or in the experienced in the space itself and the project space. He or she can build these. Like Carl mentioned, there are 2 types of requirements in a project. So this is the vulnerability type, which is ecological, quake, flood, and nuclear. And this is the attractiveness, or revulsion, I suppose, that you can have. And what I'm going to show you is some kind of key ideas that kind of will help you, at least it helped me, understand and work through these systems. Yeah. So every project has a set of constraints, and I want to explain what constraints it very quickly. Basically, when you go into a project, there are some things that you can't touch, and that could be national parks, that could be existing housing, or something like that. So you create a simple base map like this, and then I'm going to overlay the evacuation evaluation and the nuclear evaluation. Now, what you're seeing here is basically 2 systems being overlaid so that you can see which are attractive or less attractive sites for it. Yeah, and in the same way, you can do that for commercial and industrial, for example. And this way, you can, by doing simple overlays on a base map, you can actually figure out fairly quickly what are attractive locations for stuff in your design. Now, the other thing about this is the kind of the color coding, which we won't get into now because it's a separate topic. But basically, it uses a 3-color scheme, which is low attraction or high risk is red, medium attraction, medium risk is yellow, and high attraction, low risk is green. And basically, it tells the designer which places to focus on and which places to kind of avoid, essentially. Now, once you have that, if you can think of the framework, I'm going to switch to this fairly quickly. It's that, so that top row is now filled, and now we're going to just walk through the bottom row. And to do that, you kind of have to navigate this set of diagrams. And as you can see, this is a grid. We worked with, I think, 200 diagrams today, or something close to that. And so these were created by people and added to the grid. And these are individual projects or policies that help solve for that requirement. And I'm just going to show you a couple of them. This is an idea where they're saying you need to move the forests by the hillside for high radiation, because they have high radiation. And you can expand it and show it quickly over a base map, and you can see what they're trying to do. I'm just going to overlay the assessment on top of it. You can see that the reds are like really, the condition of the red portion of that is really bad, so they're suggesting to move those forests over the red. So that's how you kind of start to understand the different projects and policies. It's fairly simple to add a diagram. I can add a quick diagram to, let's say, the commercial requirement. Let's say I say a new shopping mall. What's happening here is once I add it, it's kind of being shown at the bottom. It usually goes at the bottom. So here's my new requirement, and anybody who's joined on the tool online or in person sees that immediately. And you can start to kind of see how these diagrams were created. Now, you can see some of these were created in the morning. You can see that's the Greenbelt project. And this is all democratic information, so any design team can choose diagrams from this one. So nothing is kind of personal or private information in this kind of a system. Now, the other thing that I wanted to show you was how do you create a design? And that's actually fairly simple. And we have a kind of a small set of diagrams that I'm going to choose. And so the way to do that is basically I am part of a team. Basically, here's automatic team, and I kind of start to select actually a set of diagrams, and I just started to click on the ones that I like. So you have the nuke one, and then you have Quick 1 and 4.
What do you have?
A nuke 1, quick 1 and 4. And as you can see, when I start to click on this, my design is being built at the bottom. And you can start to kind of see how your design looks, at least at the moment.
Do you want me to go further on this?
Yeah.
Okay, on ecology, I want 1 through 6.
Ecology 1, 2. So it's just a matter of just selecting a bunch of them.
I want quake 1 and 4.
That's there, yes.
I want flood 1, 3, and 5. Nuke 2, 3, and 4. Evacuation, let's try 2, 3, and 4. Replacement housing 1 and 3.
Replacement housing 1 and 3.
High density housing 5.
Yeah.
Commerce 5.
Yeah.
Industry 1 and 4. Low density housing 1.
1 and 4 and 1. And so this is my set of diagrams. And you can see that's how it looks. And this you can iterate through this very, very quickly. You can actually see, you can talk to your colleague, or you can talk to your teammate and start to remove or add diagrams to this. And this is a constraints-based map, so you can see that they're leaving out a certain kind of areas that you are not supposed to touch. And at the same time, you can see diagrams made by other people. I know Stephen had a lot of issues in his in the workshop today, but that's his diagram. And basically that's it. And this is a list of the individual diagrams. And finally, you can and this is a grid which kind of explains to you which ones you have selected and which ones Stephen selected there. And finally, you just kind of have this notion of computing the impacts of your selections across all the systems. And it's going to take some time because the number of selections is a little bit high. But what you can see here is how does your design perform with these requirements. And the idea is you go through this cycle of iteration very, very quickly to add or remove diagrams and then come up with a plan for your kind of for your team, basically. I think it's populating. There we go. So what it's done is it has taken all of your diagrams that I selected here, and then it has kind of figured out how these diagrams perform across the 10 systems. And then finally, what I can do is I can just hit save.
Hold on. There's a very primitive cost model built into this. So that design that I just specified for Rishi costs 540 million euros.
And you can actually, by changing the size of the polygons and editing the diagrams, you can actually make it, lesser or smaller. Sometimes you have targets to meet. In this case, you had a target of 5 hectares of new commercial space. We just selected one kind of polygon, so we kind of achieved. We still have 2 hectares to go. So you can do some simple target versus actual kind of analysis on these designs. And finally, you just hit save, and then you just say something like, first design of something, auto team, for example, and then I just hit that. Now, what it does now is basically stores your design so that you can come back to it, or you can start to do a second version of it. You have a discussion. And I want to show you basically some of the designs that were built in the morning today by the different teams. So they had the Soma government, the Japanese national government team, the developers had their design, and you can see some of the grids that they have used. And something's wrong with the resolution. And here's the old people team and the young people's team, and that's just an algorithm that runs and picks a design for you. And then you can do analysis, in addition to the performance, you can do analysis like this, where you start to overlay all the designs that were selected and try to see if there is a consensus or not. There are many other ways to compare, and I think Carl's going to go a little bit into it, and so I'm going to hand him back to Carl.
Good. I need my slides kicked up on here. You're still in your software. No, I want to skip a lot of slides. Okay, so so each design, we did not use City Engine, but we could easily have if we had a link to it. So each design is a series of decisions. It's a plan. It's a 3-dimensional thing, and we've got 6 of them. These are from Delft. These are the Delft ones, not today's. We can compare the decision model. We can compare the design. We can compare the component elements. We can make the frequency of diagrams. In other words, if 3 or 4 teams agree that it's a good diagram, maybe it's a sensible thing to do. We can overlap them all and look for compatibilities and conflicts. We can compare the impacts. We can index the impacts if you believe in indices. And we can tell you roughly what it costs given 25%. So that's the 6 designs. And it tells us something. We can remove some because that one didn't fulfill all the requirements. They're out. We can find the least cost one. We can find the least impacting one. We can have what this does is, see the number, I don't know if you can see them, but each box has a number of teams that pick that design. And so we can make a design based upon those which had 50% acceptance by a team that starts out conflicted. So if they pick the same diagram, maybe they'll disagree. That we can negotiate. We can basically ask each team how similar it is to each other. We could probably do that statistically, but we do it visually and socially. We can make them agree, make them negotiate. And basically, there are 2 things that this does. It says, what kinds of digital information systems do we need? Well, you need to be able to handle a whole set of design ways, but let's talk about that. I'm going to show you 8 examples of these different methods. This is anticipatory. That's a sketch I made in the middle of the night, one night. I did it on paper. I then came in and I drew it, and then I took each of these pieces and I made it a diagram. I put it on a base map, and there's my design. That's in Hrishi's system. And then I said, I think I have a lousy road. I want to change it. So I eliminated that. I drew another diagram and changed my design. That's how traditionally design works. You get an idea, you diagram it, and you develop it. This is participatory. It's not different from having 6 designs or 600 designs. Figuring out how many people agree with each diagram and making a new design of the ones that are 5, 6s, and 4s, if you have 6 teams, and that's a design of agreement. That's very similar to what Juan Carlos did in his thesis, which is one of the cases in my book of participatory design. Sequentially, I'm a very experienced designer. I know that that plus that plus that plus that plus that plus that is a good design. Leave me alone. Goodbye. Thank you. That's what it is. I'm confident. I don't need your evaluation models. I know that it's a good design. This is constraining. This is what the people mainly did today in the workshop and in our past. Basically, picking something, testing if it's good, picking something else, iterating, and building up a design. This is an interesting one. This is where the chief planner of SOMA Japan, the actual first workshop, they said, these are equal. Nuclear radiation and keeping jobs. And these at that time were the nuclear diagrams, and these were the industry diagrams. And all these combinations were compared before the design was selected. There ought to be an automatic way to do that. We've thought about it. Comparing lots of combinations and automatically picking the one that performs the best. This is rule-based. This is find the design with the least red impacts if only one diagram is chosen in each system column from available diagrams. In other words, if you solve the problem in one set of one diagram from each column, there is no design that can have fewer red impacts than this one, and that's the amount, which allows you to basically ask the question, am I in the right realm when you have something as a target that says the least impacting design in this language? Nobody can say it's the least impacting, but in this language it is. And this is an optimized one. What's the least cost solution if only one diagram is chosen in each system column from available diagrams? And it costs, in euros, 43 million euros. My design just now cost 400 million. That's 10% of my design, and it solves the problem, but it's a dumb design. Well, all right, let's put some rules on it so it's not dumb, and maybe it'll go up to 100 million euros. This is agent-based. We don't have one, but I've been talking with Kevin Johnston about building one. He did it for Redlands 3 years ago. Why can't he do it for SOMA Japan now? I have no idea, but I don't know how to do it myself. This is, in a sense, it's not agent-based. That's an error. This is a time sequence, time 1 and time 2. That's basically versioning. All that is versioning, but changing the demands on the area in different time stages so we can grow a place. And tomorrow, and on Saturday, we go off to Georgia, and with the University of Georgia, with their definitions, their models, and in 3 days, we're going to work at 2 scales simultaneously. The city of Savannah in its county, where they're building a huge container port, and the population, let's say, might double. And in it is a historical state park. And the relationship of working at 2 scales with 2 types of decision models at the same time is what that workshop is about. And then in May, we're going to work with Tim Nyerges at the University of Washington with his people and his models, working on the suburban growth of Seattle in 2 sub-watersheds that are pretty nice now, and who knows what they'll be after we're done. Now, what kinds of digital information support management? Well, something like this, at least. All of the above and a hell of a lot more, because we're just beginning. That's the reality. We're beginning, and there's only about maybe 6 to 10 groups thinking about these things. And there'll be a lot more, a lot more. This tool of Rishi's will be available on July 1st and free to use for all. What you have to do is get an account with him, and it's free to use. And it's not that different from 50 years ago. Thank you.